Hi friends, my name is Amita and in this video I am going to discuss about the power circuit diagram of an three-phase bridge rectifier circuit. Dear friends, have you think about why the power circuit diagram of an three-phase rectifier circuit is consisting of an three lags and each lag is having two diodes or two SCRs. If you see the power circuit diagram of a three-phase rectifier, all the upper devices in the lags are connected in a particular fashion and they are connected like their anodes are short circuited and they are at similar potential. Similarly, if you observe the lower devices of all these three lags, they are connected in such a way so that their cathodes are short circuited and they are at similar potential. That means the bridge rectifier circuit is consisting of an devices where the three devices are connected in a common anode configuration. They are the upper devices, and the three devices which are connected at the lower part of all three lags, they are in common cathode configuration. So my dear friends, I will tell you with the help of this video how the common anode configuration and common cathode configuration works, and when these two configurations connected in a particular fashion, then how it converts into a bridge rectifier circuits. So now I am sharing my screen and where I will tell you the importance of common anode and common cathode configuration, and later on I will tell you how these two configurations combines and converted into a bridge rectifier circuit. So, evolution of a power circuit diagram of a three-phase bridge rectifier circuit. Now, before understanding how the power circuit diagram of a three-phase bridge rectifier circuit comes into existence, let us try to understand the different kind of connections amongst the power semiconductor devices. So, first connection is common cathode connection. When we called it as a common cathode connection, suppose there are three diodes and the anode of these three diodes are connected to the three-phase AC supply. One is R phase, second diode D2 is connected to Y phase, diode D3 anode is connected to B phase, and the cathode of all these three diodes are short circuited, and through this short circuit a load is connected between the neutral and the common cathode terminals of the diode. That kind of connection is called as a common cathode connection because the cathodes are at similar potential as they are short circuited. Now, when we connect the diodes in this particular fashion, under the condition as that diode will be only forward bias, which is connected to the maximum positive supply, because the cathodes are at same potential. So under the circumstances, only that diode will be forward bias, which is connected to maximum positive supply. So as you know that the anodes of these three diodes are connected to three-phase AC supply, and three-phase AC supply is nothing but it is apart by an angle of 120 degree. So you know that three-phase AC supply is having maximum positive supply at a different instant of time. Like R phase is having maximum positive supply at different duration, Y phase will have maximum positive supply at different duration, and B phase will be having at different duration. I will tell you later on that that will be clear to you. So that means when the devices are connected in this fashion, devices can be forward bias when they are connected to maximum positive supply. They are connected to maximum positive supply means the anode is connected to maximum positive supply. Okay, that's why the devices are called as an positive group devices. Okay, so this is something about common cathode configuration. Now let us talk about the second thing, that is common anode connection. Like if we connect the devices like this and we short circuited the anode of the devices, this is load. Suppose this is D1 dash, D2 dash, D3 dash, and this is three phase AC supply. D1 dash is connected to R phase, D2 dash cathode is connected to Y phase, and D3 dash cathode is connected to B phase. So that kind of connection is called common anode connection, because the anode of these three diodes are short circuited so that they are at the same potential, and cathodes are connected to the three phase AC supply. Now since their anodes are at the same potential, so under the condition the diode will be forward bias, which is connected to the maximum negative supply. And as we know that the three phase AC supply is having the maximum negative voltage at a different duration, so D1 dash, D2 dash and D3 dash will be forward bias at a different duration depending on when the R phase, Y phase and B phase are having maximum negative value. So in this kind of connection, the devices will be forward bias which are connected to maximum negative supply, and the connected devices in this fashion are called negative group device. Okay, so summary is common cathode connection में devices are positive group devices. So what are the positive group devices? D1, D2 and D3. Whereas if I talk about common anode connection, devices are negative group devices, and they are D1 dash, D2 dash and D3 dash. Now let me draw the three phase voltage waveforms, and with the help of that waveforms I will tell you that how these devices are going to forward bias. So I am plotting three phase supply. This is the trick to plot the three phase supply. Now we are supposed to connect like this. So this is how you can plot the three phase AC supply. Now this is 30, this is 60, this is 120, this is 150, this is 210, this is 240, this is 300, this is 330. So that's the complete cycle, and it will be again, then it will be 390 and it repeats. Now if you see, this is R phase, this is Y phase and this is blue phase, and this is the center point, x-axis, and this is your y-axis. Now if you see, the R phase maximum positive between, you can see between this point to this point, R phase is maximum positive. So that means that duration is 30 to 150. Y phase maximum positive between, you can see that 150 to 270. 150 to 270. And B phase is maximum positive between 270 to 390. So B phase maximum positive between 270 to 390, and 390 ko I can write 30. Okay, so these are the maximum positive duration, and this is nothing but ये क्या है? This is 3-phase AC supply, which is the input to the 3-phase rectifier. And you can see that R phase is starting at 0, Y phase is having 0 value at 120, and B phase is having 0 value at 240. So that means these phases are repeating its value after an interval of 120 degree. So that means these are the 3 phases which are apart by an angle of 120 degree. Now similarly, if I observe the maximum negative duration phase wise, you can observe R phase is having maximum negative value 210 to 330. So that is from 210 to 330. Now similarly, if I see Y phase is having maximum negative voltage, that is 332 up to this place, or I can say 330 to 360 and 90 up to this point. So 330 to 90. Similarly, B phase is having maximum negative. You can see that is 90 to 210. So 90 to 210. So we have seen that R phase is having maximum positive between 30 to 150, Y phase 150 to 270, and B phase 270 to 390. So let us write the duration of maximum positive. R phase, Y phase, and B phase. So R phase are having from 30 to 150. You can see Y phase 150 to 270. It is 150 to 270, and this is 270 to 30. Whereas if I talk about maximum negative, R phase, Y phase, and B phase. R phase is having maximum negative 210 to 330 like this. So 210 to 330, and this one 330 to 90, and this is 90 to 210. Now, as I already told you that if you see the common cathode configuration, D1 is connected to R phase, D2 is connected to Y phase, and D3 is connected to B phase. So let us again draw the common cathode connection. So this is your common cathode connection, and here it is a load. This is D1, D2, D3. This is R, Y, B. So of course in this duration D1 is going to forward bias. In this duration biphase से which diode is connected, D2 is going to forward bias, and in this duration D3 will be forward bias. So it means positive group diodes forward bias duration will be for D1 it will be 30 to 150, for D2 it will be 150 to 270, and for D3 it will be 270 to 30. So this will be the forward bias duration for a positive group SCR. Now let us talk about negative group SCR, negative duration. So R phase, it is negative between, we have seen 210 to 330, 210 to 330. Y phase 330 to 90, and B phase 90 to 210. Okay. Now if I draw the common anode configuration circuit, connection circuit, that is like this, and you know this is connected to load like this. So this is R, this is Y, this is Y, B neutral. This is D1 dash, D2 dash, D3 dash. And what kind of connection is that? Common anode connection. So, of course, D1 negative group devices are the negative group devices. So, negative group devices D1 dash, that will be forward bias 210 to 330 because D1 dash is connected to R phase and R phase is maximum negative in this duration. So it will be forward bias between 210 to 330. D2 dash will be forward bias 330 to 90 because it is connected to Y phase and D3 dash is connected to 90 to 210. So these are the conducting or the forward bias duration of the respective SCRs connected in common cathode configuration or a common anode configuration. Now if I connect the common cathode circuit and common anode circuit like this is D1, D2, D3. This is D1 dash, D2 dash, D3 dash. Here it is R phase, this is Y phase and this is B phase. Now R phase I can connect here also, Y phase I can connect here also, B phase I can connect here, and this is load and this is neutral point and this is load and neutral point. So we have connected common cathode circuit and common anode circuit. If you redraw this circuit, we can redraw this circuit like this. This is D1 and D1 through this middle of R is connected to D1 dash. So this is D1 dash. This is D2 and here is D2 dash. This is D3 and here is D3 dash. And D1 and D1 dash के बीच में there is a R phase. So this is R phase. D2 और D2 dash के बीच में there is D2 and D2 dash के बीच में it's Y phase and D3 and D3 dash के बीच में there will be an B phase. And since these two loads are in series, so I can convert that as a series connected load. If it is Z, this is Z, so it will be 2Z. So this is nothing but it's a three-phase bridge rectifier circuit which is originated from common anode and common cathode circuit. So my dear friends, in a similar way, if in place of diodes, if we connect the three SCRs, that is silicon controlled rectifiers, in a common cathode configuration and three SCRs in a common anode configuration, and if we connect these two configuration in this particular fashion and if we rearrange it, that will be the power circuit diagram of a three-phase bridge rectifier, SCR based. Diode based three-phase rectifier is a uncontrolled rectifier, and if we make the same rectifier circuit based on SCR, it will be an controlled three-phase rectifier circuit. So now I'm stop sharing my screen. My dear friends, whatever information I have shared in this video related to a common cathode connections and a common anode connections of a device and how these two connections finally converted into a bridge rectifier circuit, that will be clear to you. And in next video, I'm going to discuss in detail about the working of a three-phase diode-based bridge rectifier as well as three-phase SCR-based bridge rectifier circuits. So if you are interested to learn those things, then keep watching my videos. If you like this video, kindly press the like button. And if you feel that whenever I make such kind of videos in future, a notification should reach to you, then don't forget to subscribe my channel. Thank you.